let's just take an aside before we do that. Okay. Now I want to calculate this. This is a quantity that is going to be needed very often. Now how do I write this in terms of F and P? What is the expression for this? Remember, the definition of phi is, phi alpha is nothing but f of xk plus alpha pk. Okay. So what do you think we can apply over here? Which of the theorems of calculus can be used over here? We can use, we'll have to use chain rule, right? So we can put in the formula, or for one time we can actually derive it explicitly so that you get a good grasp of it. Okay. So let's take simply 2 dimensions. So I'm going to write xk as a 2-dimensional vector. Let's call it x1, x2. Okay. Similarly, pk, how many dimensions will pk have to be? Also 2 dimensions. Let's call it p1 and p2. Okay. So therefore this quantity is again a 2-dimensional vector, x1 plus alpha p1, x2 plus alpha p2. Right. So d phi alpha by d alpha will be, by chain rule, there are 2 variables over here of the problem, so there will be 2 partial derivatives, right? So I'm going to have d phi by d x1 multiplied by d x1 by d alpha. Is that all? There has to be one more, right? Phi depends on x1 and x2. So there has to be one more term over here, right? What is d x1 by d alpha? x1, yeah, dx1 by d alpha. Is that what we have? Yeah. What is that? Actually, x1 is a proxy for the first variable. So when I take the derivative of this, is what? If I take the derivative of this with respect to alpha, what am I left with? P1. This is going to be P1. And the second variable over here is basically this guy. When I take the derivative of the second component with respect to alpha, what am I left with? P2. So this guy is P2. So you could also look at this as and P1, P2, right? So in compact notation, what would this be? What is partial derivative of phi with respect to x1 and x2? Grad f, right? So this is going to be grad f xk plus alpha pk transpose multiplied by, what is P1, P2? Pk. Okay. So this is a small result that we will use, because it's giving us the relation between d phi by d alpha and the stuff it is made of, which is f and p basically. Okay. Okay. So the first of the Wolfe conditions is, I mean, there are going to be 2.5, let us say, Wolfe conditions that we'll speak about. The first one is a very, very intuitive condition, which is simply called the condition of sufficient decrease. Condition of okay. So let's see what this means. Okay. I'm going to try to draw the an explanatory graph over here. Okay. So this is my alpha. This is my phi of alpha over here. Okay. Now the condition of sufficient decrease, we will come to it more precisely soon. Supposing at alpha equal to 0, I give you two pieces of information. I give you the function value and I give you the derivative. So I am giving you phi of 0 and phi prime of 0 are given, right. This is in some sense the bare minimum information that needs to be given to you to proceed over here. You are also obviously you are given the descent direction, that's been given to you, we are not trying to compute it. For example, it could be gradient descent direction, it could be conjugate gradient, it could be Newton method, that's given to us, right. So you are given phi 0, phi prime 0, what is the best that you could do? If you were only given phi of 0, the what you could say is you could draw a function like this, which is basically a straight line, right, which is a constant function value. It's like the 0th order approximation of a function, right. So this, let's call this phi a, and phi a is phi a of alpha is nothing but a constant f of xk, right. Now the other thing that you could do is, based on this and this, can I construct a model? If I give you a function value and a derivative, can I construct a little bit more sophisticated model? I can create a linear approximation. So I need these two guys, right. So if the slope here is like this, the linear model is going to look like this, right. Okay. What will be the expression for this? Won't we be simply using first order Taylor's theorem? That is essentially what it is, right. So what will it be? F of xk plus alpha times grad fk transpose pk, right. What is this term over here? If you just scroll up over here, yeah, this is d phi by d alpha of alpha. So look at this expression over here. If I put alpha equal to 0, what will I get? Grad fk transpose pk. What do I have over here? Grad fk transpose pk. So this is nothing but the linear approximation which I can construct because you have only given me phi 0 and phi prime 0, right. This is phi prime 0. So the idea of sufficient decrease is that let's write it in words over here, okay. We want that this new point that I want to reach by xk plus 1, its function value lie below the this is the intuition behind the condition of sufficient decrease, that take your function, create a linear approximation of this function at that point at alpha equal to 0, and say that whatever next xk plus 1 you choose, it had better lie below this, okay. So for example, if I picked alpha equal to this value somewhere here, this function value is above the linear approximation, so I will reject it, right, which in this case looks like a good idea, right, because the function value over here, if okay, let's not pick this value, let us for simplicity take something like this. If I pick this, then this function value would be rejected, which is fine, right. Now in practice, what ends up happening is that this condition ends up being a little too strict. So people relax it in a very simple way. They say, okay, linear approximation is probably too difficult. So what can I play around with the linear approximation? Let me change the slope a little bit. So instead of saying this full guy over here, which is the slope over here, let us say C1 times this, where C1 is some small number. So if I want to construct a straight line with a slope equal to C1 times this, where will this line lie? If you were to draw it over here, of course it has to agree at alpha equal to 0, so it's going to pass from this point. Where will it be? Will it be closer? So starting from the red line, if C1 equal to 1, I am on the red line. If C1 equal to 0, where am I? I am at the green line. If I am somewhere in between, right, if C1 is between 1 and 0, basically this is my second approximation. So I am going to call this phi b of alpha, and that is going to be f of xk plus alpha C1 grad fk transpose pk, and I am going to say that C1 is some small number between 0 and 1. Okay. What people have found in practice, C1 is actually quite a small number. C1 is often of the order of 10 to the minus 4. But this is, I mean, just some number. There's no theoretical reason why it should be so small. Okay. So this is, you can think of this as a relaxation from the exact linear approximation. So you can see that the orange line is going to allow more step lengths because more areas of the function are included. Okay. And this rule by itself is called the Armijo rule. Okay, just so that when you see it in the textbook you don't get confused. Okay, so what ends up happening is, so the Armijo rule simply is that f of xk plus 1, okay, is, or let me write it even more explicitly, plus alpha pk is less than or equal to f of xk plus alpha c1 grad of this expression. Now towards the end of this module we will talk about how do we pick alpha. Okay, so far I have not told you how do we pick alpha, we will come to that in the end. But this rule is telling us, giving us a good way to check whether or not I should accept this value of alpha. If this inequality holds, I say okay, this alpha is good enough for me. Okay. Can someone think of a problem with this rule? Now that we have stated this rule, let's also try to find what are the deficiencies in this rule. If? Okay, so question, can there be no alpha that satisfies this? If I take a very small value of alpha, will this get satisfied? It will get satisfied, right? If I pick a very small alpha, this expression will get satisfied, particularly because there is a C1 hanging out there. And keep in mind, this is the direction of descent. So that means the function value is decreasing as long as first order Taylor theorem is correct, holds true, which holds true for small values of step. Therefore, in the worst case, what will happen? This will allow very, very small values of alpha. Practically, what does it mean for you? Means you have to sit there waiting for the simulation to end because you are taking very, very minute steps. And remember, at each step, you have to then evaluate, this guy, f of xk plus 1, right? And if each evaluation is 4 hours, let us say, and you are moving 10 to the minus 8 each time, and your actual solution is far away, it's like the tortoise which is slowly going there, right? It's not smart. So one of the big problems with this is it allows, nothing prevents it from picking very, very small step lengths, right? So it allows this is a problem. Okay. Yeah, question. Pardon me? C1 let us assume to be fixed. Okay, let's assume C1 to be fixed, otherwise it ends up being the same thing. Let's assume C1 is fixed. Okay, and now we are trying to find what is the best value of alpha. Okay. And remember, there is no very good theoretical reasoning for C1, it's sort of picked heuristically from problem to problem. Okay. What people, when they would have first deployed this, they would have realized that this condition if I keep C1 equal to 1, it's a very strict condition. If it's a strict condition, what will happen? Very, very small values of alpha get chosen. Now, if I make C1 to be a smaller number, a broader range of alphas is allowed. So, it allows the algorithm to progress faster. That is the intuition behind C1. But exact choice of C1 would be done heuristically, and it's very problem dependent. So, assume it is fixed. Okay. Right. So, since it allows very small values of alpha, Wolfe proposed a second condition. Okay. And so far, if you notice, the condition only depends on the function value. Understandably, the second condition looks at the derivative value. So, it is called the curvature condition. So, let us see what this curvature condition is. Okay. I am going to try to draw it first. Let us again keep in mind what the goal is. The goal is, at the new point xk plus 1, gradient should be 0. That is the goal. Let's just quickly remind ourselves of that. Okay. And we know that phi dash of alpha is grad of fk, xk plus alpha pk transpose with pk, right. So, therefore, another way of writing the goal is phi dash alpha equal to 0, right. This is just revision. So, this is, you can say, this is the goal that we want to arrive at. Okay. So, let us write down this, again, very common sense kind of a condition. I want to proceed in the direction where the slope is reducing, right. Function value is decreasing is one thing, slope is also reducing, both are sort of mirror images of each other. So, instead of talking in terms of function values, let me go to a more direct thing, let me talk in terms of slope values, right. So, in words what it says is the value of the slope derivative at alpha, okay, be at least less than the slope of the linear approximation. Okay, and linear approximation obviously is at xk. Ideally, I want the mod of the slope to be 0, but I am saying, okay, that is asking for, if I want the mod of the slope to be 0, what am I actually asking for if I get that? Supposing I get that, what have I inadvertently, what have I asked for? Stationary point, in other words, I have asked for exact line search, and we have said exact line search, there is no efficient way of getting it, right. So, we are saying, okay, let the derivative, the slope magnitude be as low as possible. Specifically, let it be at least less than the slope of the linear approximation. So, if you think of this graph over here, if I start with the slope like this, I eventually want it to be flat. So, I am saying, okay, the slope is this much here, as I progress, at least let it flatten a little bit more, right. Having said that, with the intuition of this C1 factor over here, there is going to be another slight relaxation. I will say, okay, slope of the linear approximation may be too strict if the slope is like this. So, I say, okay, C2 times the slope. So, let us draw a few graphs over here. So, for example, let us say that okay, this is supposed to be the slope of the linear approximation. Okay, so slope, I mean, this is the linear approximation and the slope is this. Okay. Now, slope of linear approx. Now, supposing I say, okay, C2 times this slope, which way should I draw this slope now? Shallower, right? So for example, this could be C2 times the slope. So we'll call this C2 into slope, let's say linear slope or linear approximation slope. Okay. Now I need to find points on this graph where the slope is actually this, right? So think of taking this orange line like a slider and moving it around the graph to find out where in the graph is the slope actually this, right? So if I just visualize taking this as a stick and now moving it around on this graph. So it's just drawing parallel lines. For example, this is one place, right? Is there another place on this graph where the slope is equal to C2 times the linear approximation? Yes, right, further to the right. So somewhere over here, right? C2 into linear approximation slope. Okay. So what did we say over here? Phi dash alpha is less than C2 into slope of linear approximation. Okay. So what this is telling us is that between these two ranges, this is the allowed alpha, because at these points over here the slope is actually reducing, right? I started with a steep slope and now the slope is relaxing. At some point of course it is going to 0, which is my best point, okay, and then again at some other point the slope begins to increase and I reach another point. If I go beyond this point, this condition would not hold, the slope may become steeper or so on, right? So notice that by trying to put a condition on the slope, I am automatically rejecting very small step sizes. It is not, it's going to reject the smallest, alpha equal to 10 to the minus 12, right? Because it's saying that the slope at 10 to the minus 12 will be almost the same as the slope of the linear approximation, but we are saying you need to make the slope a little bit gentler. Alright.
So there's a mod, right?
Yes, so we'll come to that. So let's, the mod, okay, so the mod I put to give you an intuition about this. Let's formally write it down, okay. So this is, let's just say intuition.